them as this equation, right. So, w dot x plus b equals 0. So, b is a number, w would be essentially like if you think of a line, right. So, what is the equation for a line? Y equals mx plus c, right. So, c is some constant, m is also some constant, and it is just multiplication with x. So, this is basically the higher dimensional form of this. So, here instead of mx plus c you have w dot x plus b, right. So, x would be the coordinates of a vector, right, and so this will define a hyperplane. So, right. So, our goal is to essentially figure out the values for w and b given the training data set. So, that hyperplane that we figure out separates the positive and the negative samples, data points. So, everyone is okay with the definition of hyperplanes? Like anything that I have said so far that is unclear?
Sir, is the separation based on the value of w and b?
Correct. So, before I go to the separation of these points, I just want to make sure you are clear with the definition of hyperplanes. Yeah, and then the separation part comes here. Okay. So, if a point is positive, then what will happen is that when you substitute the coordinate of those points for x here, right. So, the value that will come out of this equation, that will be a positive number. Right. If that point was a negative data point, then the values that will come out will be some negative number. Okay. So, our classifier uses a linear separator in this form, right. So, the hyperplane itself is defined when this equation is equal to 0, it is for those values of x where this equation is equal to 0, and for other points if the value of the equation comes out to be positive, then they are classified as positive points, otherwise they are classified as negative points, right. So, this is how this hyperplane is classifying the set of points in this vector space. So, is this clear? Right. So, you already know dot product, so no need to go into this, and then dot, instead of saying writing it down explicitly, you just write it like this, right. Yeah. So, here is an equation for, so you are given a set of data points with their labels, which is either +1 or -1, let us say, that is your training data set. And from this training data set you want to figure out a linear separator, a hyperplane, which keeps, for which the equation for that hyperplane you evaluate to positive for the positive points and negative for the negative points. This is what you want to do, and here is an algorithm for doing this. So, start off with the value of w being equal to 0 and including setting b also equal to 0. Right. So, initially it is just some default hyperplane. Now, while there is now take one training data point, right. If this training data point is being misclassified, right. So, suppose it is a positive data point, but w dot x is strictly less than 0, right, or it is a negative data point and then w dot x is strictly more than 0. Then what you do is that you update w, right, you add xi yi to w. Right. So, yi is a number, this number is being multiplied with the coordinates of this vector xi, and that is being added to w. Okay. Yes.
Sir, if yi is equal to +1, then why dot product is less than 0?
No. So, the point is that the classifier is right now misclassifying this point.
Okay.
So, only when it is misclassifying the point do you do this, otherwise you do not do anything. If it is correctly classifying the point, you move on to the next point essentially.
Okay.
Yeah.
We start with B because
Right. So, sorry. So, I was going to come to this point. So, here it is here that things become a bit more complex. So, let us just go back here, right. So, in 2 dimensions when you have these points and I have drawn this hyperplane, right, you can see that, well, this is not actually an hyperplane, it is like a shifted hyperplane, it is not passing through the origin, as in this is not a subspace of the 2D space, right. So, if I have this extra b, it sort of becomes more inconvenient. So, what we do is that we sort of bring this b inside, right. So, what I do is that I take each x and add an extra coordinate. Do I want to do that? Sorry? Yeah, I will just extend this vector by adding a 1 here, right. So that I can simply write down the equation as w x. So, see, look at this equation, right. So, you have this equation for line w dot x plus b equals 0, right. So, I can simply think of this as w dot x plus b times 1 is equal to 0, right. So, then I can think of a new vector. So, let me write this down. Right. So, I am saying w dot x plus b equals 0, which is to say w 1 x 1 plus w 2 x 2 plus w n x n plus b dot 1 is equal to 0, right, which is the same as saying take the dot product of these 2 vectors w 1 w 2. So, this is the first vector, right. The second vector is x 1, wait, sorry, this should be a, sorry, this should be a, okay, this should be a b. Okay. So, I have written it like this. So, I can think of this as some w prime dot x prime is equal to 0. Right. So, I am just interpreting this whole thing in a higher dimension. Right. So, now if I do that, then I mean my life becomes much simpler. Right. So, in this way my data was in 2 dimensions in this example here, but I sort of look at it as a 3 dimensional object, where at the last coordinate I just put a extra 1, right. And then I can think of the linear separator as a like a true 2 dimensional subspace of a 3D space. Right. So, life becomes much simpler for me, otherwise I have to play with that. So, this algorithm becomes more complicated to write. Right. So, when we are saying w is equal to this, so think of this as the length of w, the dimension of w is 1 plus the dimension that we are seeing here, right. This 1 is for that extra b. Same with the data points, where x I has a extra 1 sitting at the end, right. So, once you do this, then this b in this thing, it goes away. So, there is no more, oh, it does not work here, sorry. So, there is no more b here. So, I just have this simple equation, and for once I have this simple equation form of what I want to achieve, I want to find a w. So, that for all positive points w dot x for that positive point is a positive number, and if that point is negative, then w dot x of that negative point is a negative number, right. This dot product is a negative number. This is all that I want. I want to find such a w. Then here is my algorithm to do that. Take one of these points in my training data set. Now, it could be, the label could be +1 or -1. If the label is +1, then I would like w dot x to have a positive label, right. So, what will happen is that it will have a, like, this will be less equals 0 here, right. So, then what I do is that I just add x I to w, right. I mean, just I multiply x I by y I, y is just 1 because it is a positive sample. So, x I is being added to w. Now, if it were a negative sample and this happened, it was again misclassified, then I will have w plus x I y I, right. Here y I is minus 1. So, actually I am subtracting x I from w, right. So, that is yeah.
Why we want to instead 0, sir? Directly we take xi. First is because anyhow this is 0 only will come. The first training installation w will be taken directly. W is equal to xi.
I mean, we have to start from somewhere, right, and 0 is
So
just
let's say instead of 0 you take xi now, sir.
which x I will I take?
Your training data, first data set now, sir.
Yeah, okay, sure, I can take that, but I am just saying that happens naturally in the very first. Right, so whether I do it explicitly or I start like this, immediately it will happen. That's why I mean, just for the sake of keeping this as short as possible, I didn't write that. That's what you are saying will immediately happen, right?
Yes, sir. After one iteration we will
Yes.
adjust that.
So you are saving it by one iteration, but I will have thousands of data points. So doesn't. I mean, you are correct, but it doesn't really make much difference. So this is my algorithm. It's a very simple, as you can see, it's just adding some vectors to some other vectors. Right, that is all that is doing. And the claim is that it will eventually find a linear separator for the given training data set if there is a linear separator. So everyone is okay with the algorithm? You understand the whole setup, like why B has disappeared, why blah 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 blah, everything. So shall I go to the next step? So by the way, this algorithm, as you can see, this keeps running until every point in your data set is being correctly classified with the current W. At that point you stop. As long as there is a point which is misclassified, you update W. When no point is misclassified, you stop. Right? So this is the algorithm. Now, if I don't show you anything, so it is not clear why the algorithm should even stop running, right. So I have maybe 10 data points. So I update W to fix it for the first data point. That might break W for the second data point. So update W to fix the second data point. It breaks it for the first data point, right. This can keep happening in a loop, right. I mean, it could happen, right. So because there is no other termination condition. Right. But we have this theorem which says that if the data points that are given, they admit a linear separator, then this algorithm will definitely terminate, right. And we can actually quantify how much time it will take you to terminate. That time will depend on a bunch of factors. One factor would be how much is the gap between the positive and the negative points. If they are very, very close, which means that the task of separating these 2 point data sets are it's more challenging because they are very close. So then the algorithm is going to take longer. Another factor would be how far, like how large these the length of these data point vectors are, right. If they are very, very large, that is also going to impact the running time of this algorithm. Okay.
Yeah, we are assuming the data points are linearly separate.
Yes. Yes. Because if the data points are not linearly separable, then we cannot do anything. Right. We are working in the setting where we can linearly separate the data. Right.
So how we know this is linear separable?
We don't know, but we assume it is linearly separable.
Suppose my algorithm is not converged, we can assume that it's not linear separable.
No, maybe you have some good reason to believe that the data is linearly separable. Right. Whatever data you are working with, you know something about the data, right. So maybe there is some good reason to consider that it will be linearly separable. That is all essentially. So there are also more complex algorithms which can handle some amount of noise, some point, some positive point, a few positive points here, a few negative points there. but we will not go into those complicated algorithms in this workshop. So we are simply going to assume that the data is linearly separable, and then we are going to try to find a separator for that linearly separable data. Right? So I told you the algorithm, which is just adding like vectors essentially. So let's now see the formal statement for why, like this theorem formally will prove that this algorithm terminates, and it will actually quantify how long it takes for it to terminate. Right? How many steps does it take? So let's say there is some special W star such that, I'm not sure if it's me. I'm not sure if it is from my mic or some other mic or something. Okay, so let's say there is some special W star, like we wanted to find a W such that for each data point W dot x, each data point xi, W dot xi is positive if the corresponding label yi is positive, and W dot xi is negative if the corresponding label yi is negative. So then I can also state this as saying W dot xi times yi is always positive, right? That is the kind of W you want to find. Now I am saying suppose there is some special W star which additionally has the property that W star dot x times yi is at least 1. Right? So whatever solution you find, which could be some W, this could be some number which could be say 0.05 or minus 0.05, right. So that is not suitable for this W star. So W star has to have this property that it is at least 1, right, which is to say W star dot xi is at least plus 1 for the positive samples, and it is at most minus 1 for the negative samples. Right. So can you tell me, if I give you some W, how could you compute a W star out of it? Suppose I give you one W which satisfies this thing. The W dot xi is positive for all positive samples and W dot xi is negative for all negative samples. Then how do you get a W star from this W? What do you mean by averaging?
There are number of data points to be divided.
So why will that ensure this property?
Means that will gives us a mean type of thing actually. It will be error, not minimum actually, but somehow error will be less.
No, what can you maybe give an argument for why this will work?
And that's time telling, I don't know actually.
No, that's okay. So I mean, whatever argument you're thinking of.
Means there are different W possible for that choice actually.
Okay.
I'm taking for each of the data point, that is training data point. I'm given W1, W2 and W100 suppose.
No, you are given only one W. W is a vector.
Yes.
You are not given some 100 Ws. You are only given one W.
So we additionally add only one. Suppose it's n by n measurements, we give the one. Extra one times by add one.
You want to add one.
Because suppose n vector means.
Okay. So
I
for
take
the
W.
positive. Okay. So for the positive samples.
So W is n vector, length is n, sir.
Yeah.
I think the W star is n plus 1, final is 1.
Final is 1. Okay. So then what impact does it have on this equation for W star? So if xi yi is a positive sample, so then what will happen to W, this W star that you gave me times xi?
That will be more and more. If we keep growing,
It will keep growing, is it?
like, as in like the value of W star xi ya will be more than 1.
Okay. Because you have added extra one. Okay. Now what if this xi is a negative sample, then what will happen with this construction?
The value will decrease.
So if the value was minus 0.5, what will you get now? Why?
W's are positive.
So the
only,
YA
most
is
one.
all negative, no? -1.
Right.
So xi into the -1.
But you're not multiplying xi with yi. Multiplying first taking the dot product that gives you a number. You're multiplying that with yi. Another way of saying this is that w dot xi is a negative number.
Even I is the ith row.
No. Oh, sorry. Okay. I is okay. So just say x, y is some data point. Forget I. X is a data point.
Okay.
Xi was some like you have like one of the data points.
Ith row data.
Yeah, it's not the row. It's just one of the vectors in your data.
Yeah, I understand.
Okay, so let me tell you what you should do. So you have some w such that w dot x times y is greater than 0. Right. So this takes care of both positive and negative samples. Right. So I mean you are given such a w. Right. Why does it take care of positive and negative samples? Well, for positive samples y is +1. So w dot x is also a positive number. So positive times positive is positive. And if x is an x y is a negative pair, then y is -1, right, and w dot x is a negative number. So negative times positive, negative times negative is a positive number. So in both cases, w satisfies this equation, and this w is given to you. From this w, you want to get another w star, which will satisfy this. So you are given a w that satisfies the thing on the left, you want to get a w star that satisfies the thing on the right. So the way to do it is, you go over each choice of this x y, all the training data points you have. For each data point you see what is the value that you get, right, and take the minimum. Take the minimum value that you get out of this expression. This expression, say that minimum is some lambda. So, if I take this equation and divide, if I write, then what value should I expect for any x y? I should expect at least 1, right. So, this is something you can easily prove, right. If you are not convinced, you can go and try to prove it, and you will be able to prove it.
But the theorem actually assumes that the w xi y is greater than 0 or greater than 1.
Yes. So, the theorem starts by assuming, suppose there is a w star which satisfies that thing we want,
Yes.
right. So, I am saying how do you get this w star? To get this w star, you can start with a w. I assume that the data set was linearly separable. So, there was some w which satisfies this equation for every data point. From that w, I will find out the minimum value of this expression and divide by this expression. So, w star is simply w divided by lambda.
Such a w.
Yeah. So, that would be the w star, and this w star will satisfy this requirement as we want it. So, therefore, the assumption of this theorem is it is simply assuming that my data is linearly separable, that is all. Okay. And in particular, we would like to choose some w star which has small values in it, but I mean, okay, that will come out later, right. So, but the thing is that we can start with some w star, and this existence of w star always comes out of the assumption that our data set was linearly separable. So, suppose we have this, then the claim is that perceptron algorithm. So, let me just go and remind you once, which was simply this, that whatever w you have, you run through the data set. If any particular data point, here x I is a vector and y I is also a vector. Okay, so, it is written like this here. If any particular data point is misclassified, then just add x I times y I or x y to w. right. So, for positive samples which are misclassified, w will become w plus x. For negative misclassified sample, it will become becomes w minus x. Right. This is how you change w for a misclassified sample, and you keep doing this over and over again until everything is correctly classified. Right. So, this keeps running in a loop. So, this theorem is saying that algorithm which keeps running in a loop will run at most these many times before it stops, where this many times is the first is the length of this w star vector that we just derived. Second, this r square is the length, r is basically the length of the largest vector in your data set, the largest x in your data set. Right. So, the running time or the number of while loops that will happen in this algorithm, that will be at most this much, the square of the product of r and w star, right, length of w star. Okay. So, let us try to, yeah, so r is defined here. So, let us try to prove this, right. So, the proof essentially works by keeping track of two quantities, right. The first is that, okay, so here w star is the thing that we have from here, right. So, and while we are running the algorithm, we have this vector w which is always being updated, right. So, what we do is that we keep track of these two numbers. First is just the length of w that we have in the algorithm. Second is the dot product of w and w star. So, let us look at these two quantities as the algorithm keeps running. Right. So, the first claim is that every time we update w, this quantity w dot w star, which is the same as writing w transpose dot w star multiplied with w star, that increases by at least 1. Okay. Each time I update my vector w, this quantity, this w dot w star will increase by at least 1. Okay. So, what is the reason for this? So, because I have updated w, so w has now become w plus x y, or I here is basically so x y, right. So, if I expand this out, what do I get? I get this term, the dot product with the previous w, and then this. And what do we know? We know that this is at least 1, right, by this, right. So, this value has gone up by at least 1. So, this is a very straightforward consequence of what we had in the theorem, like our assumptions in the theorem. Okay. So, the second quantity that we keep track of is just the length of w. So, the claim is that the length of w increases by at most r square, where r was the length of the largest x vector. Right. So, how do you measure the length? So, how do you write down r square, or how do you write down w square? So, that is simply w times w, right. So, when I update w, then it is w plus x I y I times like dot w plus x I y I. If I expand this out, I get the length of w square, I get this quantity, and then I get x I y I square. Now, if you look at this quantity here, I claim that this is a negative quantity. Why? I mean, this is at most 0. Why? Because I updated w, which means that this point was misclassified, right. So, if you look at this, so this is y I is just a number, I will just pull it out here. So, 2 y I times x dot w, right. So, if this was, I mean, if x, or you can look at it here, right, because the point was misclassified, this quantity is less than 0, it is negative, right. Here we were assuming that everything is being correctly classified, that is why it was positive. Because it is not being correctly classified, it is negative, right. So, this is a negative quantity. So, if I just drop this negative quantity, then I just have w square and this square, right. Here y I is just plus 1 or minus 1, so it has nothing to do with length, and this is just the length of xi square whose maximum value is r square, right. So, whenever I do an update, this quantity w square increases by at most r square. Okay. So, everyone is fine with this and this point. Yes.
So when you say that the length of the wave keeps increasing, do you mean that the vector gets more and more weights added into it, the weight vector?
I mean, it does get added or subtracted, right? I'm
not
not saying
if the value changes, but
yeah.
what do you mean by increase in the length of the vector? In the
So, w is a vector, right, which I changed by adding xi.
Yeah.
So, then I get a new vector.
Yeah, but why is the length changing? I'm not understanding that.
What do you mean? If I take a vector and add something to that vector, won't the length of that vector change? The new vector change? Is the length of some a plus b the same as the length of a? That's all. I am just bounding the length of a plus b. Right? This is the like the increase in the value of this vector when I make an update to it. And by making an update to it simply means that I am adding something to the vector. Like adding this vector to that vector. That's all. And I'm not saying it is increasing by at least this, but rather by at most this. Okay. So it might even, in fact, does not increase at all, or decrease or whatever. But it does not increase by more than that. That's all. So let's see how we can leverage, these two things to get what we want. So let's say this perceptron algorithm makes some m updates. Right. So then the first fact, which was saying that in each update the w that you have times dot w star would increase by 1, right. So if you make m updates, then the current w dot w star would be at least m. On the other hand, the length of the w, like the length square of w, that would be at most m times r square. So what I can do is that I can basically try to substitute for m. No, sorry, I want to substitute one of these things into this other equation and get some relation on m, right. So I can write down, so this is the equation that is being written like this, right. So why can I write this? Because m is upper bounded by the value of the dot product of two vectors. Dot product of two vectors is length of those two vectors times some cos theta, the angle between them, which varies between 0 and 1. Right. So therefore this is definitely true. This is the consequence of the dot product, right. And then I move this length of w star over here, right, and I replace the value of w from this equation, right. So I get this. So therefore when I so what do I get? I get a square root m here. So I can divide by square root m, and then I get this root m is at most r times w star, like the length of that vector w star. So if I just take the square, then I get m is at most r square times the length of that w star square. Right. So the number of updates that can happen in the perceptron algorithm is upper bounded by this. After at most these many updates, it has to terminate and find some linear separator.
Then also the update is also dependent on the W star.
Yes, the number of updates required to reach a solution depends on W star. So as I said, W star essentially is a function of how close the positive and negative points were, right, which came about because how did I write W star, right? If you give me a W, I will divide W by some lambda, which was the minimum distance between the separator and some other point. So if the points are very close, then that minimum distance is also smaller and smaller, which means 1 by lambda is larger and larger. So the length of W star would be larger and larger. So this is the algorithm itself is very simple, just add some vector or subtract some vector or something. But It is just very interesting that it terminates, and in fact you can prove some explicit bounds on it being it terminating essentially. Right. So I think I will stop here. So essentially there are more things to say about, because there are multiple linear separators between two set of points. I mean, take any line slightly twisted in this angle or that angle, shifted a little, right? You'll get another separator most likely. So which one does the algorithm finds? So the algorithm finds one of these things arbitrarily. We don't know. So if you would like to find a line maybe which is sort of equidistant from positive and negative samples or some other criteria like that, then you have to come up with a more complicated algorithm. So we will not go into that. We will stop here. But this is an example of how, using very simple linear algebra, you can come up with a classifier, and you can even prove that this classifier finds a solution like essentially fairly fast. So one of the things you may notice is that the time required for it to converge to a solution is not dependent on, for example, the dimension of the data. You will pay for the dimension in doing all these dot products and other things, but it does not figure in the number of updates that you have to do.
So the perceptron algorithm uses to find the best separator.
No, it will not find the best separator. So for that you need something else called support vector. So we will not go into that right now. Maybe in a later lecture or maybe not, I am not sure, but yeah, not today. Okay, so any questions? I think I may have gone a little fast in the proof part. I also don't know if I'm missing the online stuff. Okay. Right, so if you still are not sort of convinced by the proof, I would encourage you to just go through the proof, like everything is written here. You can just go and verify step by step, and if something is not clear, you can maybe ask me tomorrow. Right.
So given a bunch of data, is it possible to figure out what the number R?
You can estimate that R, right? So as in let's say you go over all pairs of positive and negative points, right, and find the closest positive negative point pair. So then R is likely to be, oh, you said R is the length of the largest vector. You sorry, I got confused. Let me just, so R is simply this.
Oh, sorry.
So I guess you are talking about W star, and I was answering about W star. Yeah. So for W star, you just maybe find the closest pair of positive negative points and take half their distance. Right. So then one over that is roughly going to be the value of that length of W star. I mean, it won't be exactly that, but it will be proportional to that.
So then, so we've given a bunch of data. Let's say we don't know whether it is linearly separated, whether there is a linear separator. But what you are saying is that there is a certain bound for that norm W star which you can compute.
Yeah.
There is, if it were linearly separable, there is some bound that you are able to compute it with.
Yes.
So now you just take this, you run the perceptron for those many iterations, and if it hasn't found a separator at that stage, would you be able to conclude that the original data was not linearly separated?
Yes. Although what I said about the estimating the value of W star, that's not completely accurate. So there are more accurate ways to estimate that value. You use that value, that will tell you that the data is not linearly separated. So here there is another factor, that your data in the real world, it's not always like the data actually is linearly separable, but there is some noise in the data. So then that noise affects various things. So then your algorithm has to be somewhat more robust to handle the noise. Like if the noise is very small, as in this point is shifted here and there a little bit, so then that does not affect linear separability. But if there are some points with a lot of noise, so that this guy goes over there, then those things become challenging. Right? And then there are other more complicated ways to handle those things. Like you have to label some things as outliers and blah blah blah. Like there are other things you have to do. But the very basic thing is essentially linear. Okay, so let me also say one more thing here, which is that, so if you go back to this situation, right, which is more representative of the real world, right. So if you have some data like this, right, you cannot, naturally there is no linear separator. Right. So let me actually give you a more better example. So let's say you have some negative data points in 2 dimensions, right, and then you have some positive data points. So there is no way that this is linearly separable, right? You can never find a line which has the negative points on one side and positive points on one side, other side. So what do you do?
Separate transformation x square.
Correct. So from this example should be basically, right. So here your data points are in the form x, like these are some xi, yi. Okay, I should not write xi, y. So the data is in the form of x1, x2, right? Like 2 coordinates in this thing. So if I have to convert this data into 3D, where it will become x1, x2, and the length so of this x1, x2. So square root of, no need for square root. X1 square plus x2 square. Once I do this, the picture will sort of look like this. So I am basically projecting these points in 3 dimensions. So these green points, they will become a circle over here, and the red points will become another circle over here. And in this 3D space, you can find a 2D plane separating the green from the red. So there are ways to deal with non-linearity in the data. Essentially, we're projecting them into higher dimensional spaces or things like that. So we'll go into those things later. But most of the machine learning algorithms, the way they work is that they take the data point which is in some space. I mean, you tried your best to come up with a good representation for the data, right? Unfortunately, that representation still does not make positive or negative, whatever you want to do, like as linearly separable. So then you have some other machine learning model, some neural network or some support vector machine or something. So the first part of that, what it is going to do is that it is going to basically keep projecting the data into more and more different spaces, and eventually it will project it into some space where positive and negative samples are linearly separate, and then it finds a linear separator between them. So this linear separator thing is essentially at the like it's the starting point of all these algorithms. That's the last thing that you do essentially. But anyway, so this was, but that circle thing is a good example to keep in mind. Okay, so let us stop here. check one second. I must have booked something. One second.
Yeah.
Did you book it?
Yeah.
Okay. So I was surprised to see.
Oh,
He's here.
no, that should that be.
Yeah, I'll come down in 2 minutes.
Not 2 minutes here.
Oh.
In the card.
Okay. I'll call you once I'm outside. Yeah? Okay. Okay, thank you. Okay.